All right, guys. I seem to be losing a lot of people. I have a very fun day planned for you. Very short lecture, and then we're going to be doing a workshop on example 1.3.2 and 0.4, if I remember correctly, just after adiabatic. And I'll give you these 1.33. And I'll give you these in groups to do. And we're going to be doing some communication work, some maths, some thermodynamics, all in one go. Anyway, start with polytropic processes. I'm going to go through the full, so if you look at your notes, there's it doesn't go through the whole math derivation of it, and I'm going to go through it. And the reasoning is I'm going to get you to do the derivation for the other parts yourself in this class as in a workshop. It's going to be fun. So what is a polytropic system? So your PEB changes in a polynomial fashion, right? In a parabolic fashion, rather. It resembles more of a real-life approach. So polytropic law. Your PV to the power alpha, your polytropic index equals the constant. Now this constant, and you know PV equals nRT, your nRT is the constant. And if alpha equals 0, it's an isobaric system. Right? PV equals nRT, V equals 1, so no change. If alpha equals infinity, it's isochoric, so isobaric, pressure changes, volume. Infinity, isochoric, no change. And if alpha equals gamma, it's an adiabatic system. So remember gamma, Cd over Cp minus 1. And if alpha is between 0 and infinity, it's polytropic. So, solving for polytropic. Now, you can see from the graph, what a polytropic system looks like. So your P and V are changing at the same time, but there is also sometimes heat transfer. It's more of a real life scenario, and the ratio determines whether it's a polytropic or adiabatic system. So, if we start from volume work, equals negative V2 over V1 PdV. To getting more people. Your P1 V1 to the power alpha equals P2 V2 alpha equals PD alpha, right? That's quite straightforward. Now we know that P equals constant over V alpha. And if we drive the equation using that constant, volume work equals negative the constant V2 over V1 dV over V alpha. Remember, C is constant. We can drive this equation. Yeah. Now, actually, ignore the alpha on the P1 V1. That shouldn't be there. So it's P1 V1 integral V2 over V1 dV V alpha. Right? So when you drive the integral, it's volume work equals negative C V minus A plus 1 over negative A plus 1 V2 over V1. Following that? If you swap that around, and take your 1 minus A out, so flip it. Remember your power rules. P1 V1 over 1 minus alpha, V2 1 minus alpha minus V1 1 minus alpha. Yeah. And your volume work equals negative P1 V1 1 minus alpha, V2 1 minus alpha minus V1 1 minus alpha times 1 over V1 alpha to gain the equation in your notes. Now, it's just a form you can put it in. It's just a mathematical form. And I'll go over why it's useful in a second. So what does that mean in terms of polytropic process relationships rather? So in an ideal equation state, PV equals nRT, and we know P equals RT over V, and V equals RT over P, right? So since PV alpha equals a constant for a polytropic process, then RT over V1, if you plug in for P, equals V alpha, equals a constant. So TV alpha multiplied by V to the negative 1, because you brought your denominator up, equals C over R. So C over R is your constant. Now you can cancel out and basically call that a constant. Hence T1 V alpha minus 1 equals T2 V alpha minus 1. Yeah? So T2 over T1 equals V1 over V2 alpha minus 1. So you have a new relationship. So you can calculate temperature and volume based on this relationship. And if you plug that into your previous equation, volume work equals negative P1 V1 over 1 minus alpha V2 over V1 1 minus alpha minus 1. Yeah? Hence, volume work equals nRT1 over alpha negative 1 T2 over T1 minus 1. So you change the relationship. Now you can calculate for temperature, and your P1 V1 equals nRT1, right? Just going over for volume this time. PV equals nRT, P equals RT over V, and V equals RTP. Since PV alpha equals constant, again, you plug in for volume. You get TA over PA, P minus 1, so you can bring your P down to become negative 1 to give you that constant. And you calculate for, you get rid of the alpha on the T by bringing it down. So it becomes T P alpha minus 1 over alpha equals CR. Now, you see something very similar in your notes in your study guide. So if you solve for T2 over T1 equals P2 over P1 alpha minus 1 over alpha, you can plug that into your previous equation, and you get what's in your notes. Volume work equals negative P1 V1 alpha minus 1 multiplied by 1 minus P2 P1 alpha minus 1 over alpha. That was the three polytropic relationships and the volume work polytropic equation. Sure, that's it.